Okay, the title of the second and last talk of CANS 2022 is Post-Quantum Electronic Identity, Adapting OpenID Connect and OAuth to the Post 2.0 to the Post-Quantum Era. It's a joint work by Frederico Schardong, Alexandre Giron, and Fernanda Muller. And Frederico will give the talk.
Yes, thank you. Hello, everyone. So my name is Frederico. I am a PhD candidate at the Federal University of Santa Catarina in the south of Brazil. And in this work, this is a very applied work. So I'm going to talk to you, I'm going to present those two protocols and show how we change them to be quantum secure. So to be clear, what are our objectives with this paper? We want to suggest modifications to OAuth 2.0 and OpenID Connect and their underlying protocols to make them quantum safe. And we do implement and evaluate the effects of post-quantum cryptography on a realistic OpenID Connect study case. So OAuth 2.0 came out in 2012. It is used daily by tens of millions of people. So every time you go online and access a website and you have to authenticate, and you do authenticate with Google or Facebook or any other identity provider, you are using OpenID Connect and OAuth 2.0. So OAuth 2.0 works with this setup. So we have a user, which is called a resource owner. It acts as a service. For instance, you are accessing a car rental website. This is the client application. The client application wants to know who you are. So it wants to use an identity provider, an external identity provider, and it might present to you a few options like login with Google, login with Facebook, and any other identity provider. You choose whatever you prefer. And then you are redirected to what OAuth 2 calls the authorization server, what we can call it an identity provider. And then it will show to you a web page where you will provide your information, user and password, perhaps a second authentication factor. So there's a communication. It will show a web page to you from your identity provider that you trust. You perform that authentication if you're not authenticated already. And then finally, the authorization server, Google, Facebook, or whatever, will send an authorization grant to your client application. And with that, it can access a research server using an authentication token, an authorization token. And OAuth came up with this idea that, well, perhaps you might have two different servers in an organization where one is concerned with the authentication and authorization and your resource resides somewhere else. So we can kind of see those two in the same organization, most of the time at least. And let me go back a little bit. So this is OAuth 2.0. And OpenID Connect adds a little bit of extra on top of this workflow. So what OpenID Connect does is that it allows the client application to be sure that it can ask the identity server, the identity provider, in a standardized way for your attributes. So let's say your client application, your car rental website wants to know your name and your email. If the identity provider is using OpenID Connect, then OpenID Connect standardized the name of those attributes. So your client application doesn't have to have a bunch of if analysis for each of the identity providers. You can have the same code for all of the identity providers that do use OpenID Connect. It also provides some other guarantees, like your client application wants to ensure that you're using multi-factor authentication. So OpenID Connect allows your client application to specifically request for users to use a second factor to authenticate. So it's just a little bit of extra. OpenID Connect and OAuth 2.0 do have some very well-known attacks. For instance, you can have someone guessing the user password. You can have malicious person or entity trying to fabricate those access tokens. The user might unintentionally grant too much access scope. So what would that be? Is that a client application basically asks, okay, I want to know everything about this user. And then the person that is on the other side of the screen kind of doesn't read that, just accept anything, and then your identity provider will just forward all of your information. You might have someone eavesdropping your tokens while they go through in that workflow. And there are dozens more possible attacks which are documented on this RFC. There are basically two large countermeasures for those problems, all of those problems. So the first one is kind of obvious, just use TLS for any communication or most communication-related threats. JSON Web Token is also indicated for stationary-related threats. So JSON Web Token is a standard that uses JSON to express tokens. So you can put whatever information you have on a kind of dictionary structure. So you have a key and a value. And the JSON Web Token standardized the idea that you have a header. Part of this JSON is a header where you specify the algorithm that will be used to sign this token and maybe encrypt this token if it is encrypted. And there's your payload, and at the end, the tail where you have the digital signature or any other information. And finally, this one comes from the OAuth 2.0 RFC, which states that the probability of an attacker guessing a token must be less than or equal to 2 to the power minus 128, and ideally less than 2 to the power minus 160. So how do we do that? It is up for whoever implements the protocol to ensure that. So the RFC just say, please make sure that this happens. So obviously, we have the quantum threat. So if someone comes up with a cryptographically relevant quantum computer today, we have a big problem in many protocols, and OAuth 2 and OpenID Connect is not an exception. More precisely, we have a problem in the key exchange part of TLS. We also have a problem with the digital signatures that happen in TLS and in the JSON Web Token. And what I'm going to show now is how we think you could kind of solve those problems in the case of OAuth 3.0 and OpenID Connect. But before that, let me talk a little bit about how we looked at the literature. So we performed a systematic literature review. So we came up with this search string where we basically tried to find any work that was attacking this issue. So we basically have lots of keywords, so OpenID, OIDC, OAuth, JSON Web Token, and post-quantum, or the techniques, or the algorithms names. So anything that came up that satisfied this search string, we ran this string in multiple databases, IEEE, ACM, Springer, and the only work that came up that was actually trying to do something similar to what we are doing is this work where these authors, they accessed the JSON Web Token. So what they did is they created some random data, put that in the JSON Web Token format, signed this JSON Web Token with dilithium and qTesla, created a server and a client in the same machine that exchange those tokens. So it created tokens and exchanged with the client, all of that in the same machine. And what they found out is that the dilithium had a better performance with respect to qTesla. But again, it was a not realistic network scenario at all. So our contributions are, so what we propose are 4 points. So the first one is kind of obvious. We have to increase the probability of someone guessing the token based on the Groover's algorithm. So the RFC should change to, instead of -2 to the power 128, 2 to the -256, and preferably less to the 2 to the power -320. So if someone opts to use encryption in the JSON Web Token, so this person should use 356-bit AES block size instead of 128, which is what the RFC right now states that is the default size for AES. The same is true for TLS, and finally, we have to use post-quantum digital signature schemes for both JSON Web Token and TLS, and I didn't add to this slide, but we should also have a post-quantum key exchange algorithm in TLS as well. So let me talk a little bit about how we evaluated, how we created a scenario that we deemed to be realistic and how we perform our evaluation. So what we call a real-world evaluation or a real-world case study is the following scenario. We have a user that opens his web browser, it goes to a web page, let's say the car rental website I was saying before. It tries to access a protected page, and then it is prompted the identity provider authentication page. The user then provides his username and password. So that whole OAuth 3.0 flow that I have explained before happens in this second step. After that, the user does get access to the protected web page. After that, the user logs out. And if you open if you perform those steps in a web browser, you would see pretty pages. So we are using CSS and JavaScript. So we have one JavaScript file for each of the web pages, and we have one CSS file. So we try to use what we have seen to be the most common. So we have a jQuery JavaScript file and a Bootstrap CSS file. Our pages do not have any images, so there is that. But overall, we do believe that is a realistic scenario. So with regards to our experiment plan, we're trying to measure two things. So we're trying to measure the size of the messages exchanged and the total elapsed time to run our scenario in both pre-quantum and post-quantum key exchange algorithm and digital signature algorithms. So by pre-quantum, we use RSA and ECDSA, and by post-quantum, we use NIST's 4 candidate algorithms of the 4th round. So Kyber for the key exchange, and Dilithium, Falcon, and Sphinx for the digital signature. So our realistic scenario, we executed 1,000 times, so it is automated. So we do not go there and press the buttons and move the mouse as a user. We have an automated script that does all those steps without any time delay, so it just goes as fast as possible. And we execute our realistic case scenario 1,000 times for each algorithm and for each of those latencies. So what do I mean by that is that we ran our case study with RSA 1,000 times in 30 milliseconds, then ECDSA 1,000 times in 30 milliseconds, and then Dilithium 1,000 times, so on and so forth. The source code is open. Anyone can download, try and experiment. So not only the code for our changes, but the code for our experiments is open source and publicly available. It's quite easy to reproduce. It uses Docker containers and Amazon machines, so you just have to pay a few cents and you can run all of those tests by yourself. So talking a little bit about the results. So for the pre-quantum algorithms, which is what this first column shows, all the algorithms, the second column shows the size of messages exchanged during the TLS handshake part of the communication. And the third column shows everything above the TLS handshake. So after the handshake is finished, all the HTTP, all the JavaScript, CSS, everything that is sent around the network goes on that column. So with ECDSA, we can see that we have about 0.04, the amount of communication, only 0.04 is expand on the TLS handshake. So most of the communication is the study case scenario per se. So not establishing the secure channel, which is a similar result to RSA, 0.08. And when you go to the lithium, 2, 3, and 5, we go an order of magnitude. We expand an order of magnitude more bytes with the TLS handshake with regard to everything else. So the result is quite similar between the different security parameters. Falcon is the same. We do expand a little bit more, about an order of magnitude more, with TLS handshake with regards to to everything else. An order of magnitude more than the pre-quantum algorithms, and then with Sphinx, we have a quite bad situation because most of the bytes exchanged in our communication are dedicated to closing the secured communication channel by TLS. So we have an order of magnitude more bytes than the ratio with regards to the other algorithms. So we have even more communication, even more bytes being sent around to close the secure channel than to send our web pages and web tokens and all of those things. Perhaps this is the most interesting result of this work. So let me go through this graph, which has a lot of information. So in the y-axis, we have the amount of seconds for each of the executions. So each stacked bar represents the mean and the standard deviation of 1,000 executions of a realistic study scenario for each algorithm. And within each algorithm, the latency between the user and the OpenID Connect server and our third party, our car rental website in our example. So for RSA, ECDSA, the Lithium 2, 3, and 5, Falcon, with respect to the user perceptive, when we are talking about 30 milliseconds and possibly less, we will have pretty much no noticeable difference. But when we are talking about Sphinx, we have about 100% more time to run the entire execution. So probably the user will perceive that is much lower than other algorithms. There are other interesting things that this graph shows. For instance, the amount of information, the amount of time, being spent to close the TLS tunnel with regards to sending all the information after the TLS handshake is finished. So let's look at, for instance, RSA and SCDSA. We have less than 50% of the communication. Doesn't matter which latency scenario we have. Less than 50%, maybe 40, 30%. Is spent on closing the TLS tunnel. But when we look at Sphinx, for instance, we have way more than 50%. It's about 80% in the worst case scenarios. The amount of time we spend closing the TLS tunnel instead of sending all the communication around. I guess that's it. In conclusion, so TLS cost, both in terms of time and size, constitutes a considerable portion of the cost, particularly when network latencies are greater. So just to give an idea of what 30 milliseconds is. 30 milliseconds is about a 2,000 kilometer distance, at least in Brazil. We don't have that many hops between the states. It could be less distance in Europe or other areas. And 140 milliseconds is the time that it takes for a package to go from Brazil to North America to the United States. 225 milliseconds is from Brazil to Europe, and 320 from Brazil to Japan. So it's pretty much the worst case scenario you could see on the internet. You couldn't get any worse than that. Our real-world evaluation has demonstrated that post-quantum cryptography algorithms do not decrease OpenID Connect performance in lower latency scenarios. By lower latency, I mean 30 milliseconds or less. We found no significant variations in performance between post-quantum cryptography algorithms of varying security levels. So that is what I mentioned before. So let's say, for instance, if we look at Falcon, we have pretty much the same amount of time. It doesn't matter, of course, comparing the same latency scenario, the same distance, and the same is true for the lithium. So it's a pretty noticeable amount of time difference between the lithium 5 and the lithium 2. But that is not true for Sphinx at all. So we do perceive a difference in higher latency scenarios when you're looking at Sphinx 192 and Sphinx 256. So since we simulated actual setups, so we used signed certificate transparency, OCSP stapling in the certificate. Of course, the whole PKI we created using the post-quantum algorithm, so all the signatures are post-quantum, the whole PKI is post-quantum. We concluded our finding provides an upper bound on the TLS costs when evaluating it as a drop-in replacement for post-quantum cryptography in OpenID Connect. So why do we say it's a worst case? Because for each communication in our realistic scenario, we did something that is not quite common, which is we do make a new handshake for each HTTP package that is, for each new communication that is closed to send an HTTP package. So that is not quite common. Most servers will use the keep alive feature of HTTP to ensure that the TLS connection is not closed. So, but we did not do that. We on purpose create a new TLS. We do perform a new TLS handshake for each package that is sent around, HTTP package, of course. So that's it. Thank you for your attention, and a special thanks to the CANS organization, the TAI, Emmanuel, and everyone on the TAI side of the force. Thanks for providing the funds for us being here. Thank you.
Thank you, Frederico, for your talk. We have time for questions. All right, we have several candidates. So is there a microphone? OK, microphone is arriving. Yeah, let's start with Maxime.
Hi, thank you for the talk. Were you using TLS 1.3?
Sorry, if we are using TLS 1.3?
Yeah.
Yes.
And did you use early data?
Did we use what?
Early data?
I don't know what that is.
Zero RTT?
I think we did not use, but I'm not sure.
OK, and how long was that certificate chain? Like only one certificate, or did you send multiple ones?
So for each communication, for each HTTP request that is performed, we do perform a new TLS handshake, yes, which obviously means that you have to send the certificate again around.
Yeah, but you usually do not send one certificate, but you send like the whole chain out the root certificate.
Yes.
So I was wondering, like, if you send a chain of length 1 or 2.
We are sending a chain with 3 certificates. So we have a root CA, middle, and the third, and then the server certificate. So we have 4 certificates being sent around.
You usually do not send for root certificate, but
yes, that's true.
Okay, thank you.
But that would be, well, a small portion, but you're right.
Okay, another question.
Are you aware of the CAM-TLS work, and is there a reason not to consider it in your experiments?
We are aware. There is no particular reason why we haven't chosen to look at it. It was just a design decision at the beginning of our work. We decided to go this way. We don't have any particular strong opinion on why we haven't used it. We just opted for not using it. But it's a future improvement. One can go that way and compare. Sure.
Thanks.
All right. Are there other questions? Go ahead, Manuel.
So I asked a similar question in another talk. Maybe you weren't arrived yet. So since PQC signature standardization will have another call for proposal, and signatures allow for several trade-offs, I was wondering if you have any advice of what should be the most important part of a signature, if the signature size, the public key size, timing for signature verification?
Yeah, okay, that's a great question. In this particular case of this protocol, the size of the signature is what has the most impact, because you do very few signature operations and a few verifications as well. So you do send signed objects around quite often, but you do not, you check them once and then after that you don't worry too much. So what was the first part of your question?
What's the most important part of this?
Yeah. Yeah, the size, yes. For this particular case, OAuth 3.0, I would say is the size of the signatures, yes. No problem.
There is time for a final question, if any. Okay, looks like we can thank Frederico again.
Thank you.
And actually, let's thank all the speakers of CANS 2022.